Okay, now I would like to explain about series aiding connection and series opposing connection. So first one, series aiding connection. Okay, here two inductors having inductances L1 and L2 are connected in series connection. So the current flowing through these two inductors is same. It equals to I. So this is the first end of first inductor and it is second end of first inductor and it is first end of second inductor, second end of second inductor. So here both inductors currents entering at first end. Okay, here at dot the current entering into the inductor. Here current entering into the inductor, and in second inductor from this point current entering into inductor. So this connection is called series aiding connection. So let us consider two inductors L1 and L2 which are connected in such a way that flux produced by the two windings is aiding. So whenever the AC voltage applied to the circuit, current I starts flowing in a circuit and the voltage is induced across the inductors, the induced EMF is equals to E1 and E2. So E1 voltage across the inductor, E2 voltage across the second inductor. First inductor voltage E1, second inductor voltage E2. Okay, now apply KVL to the circuit. Okay, we know that the KVL statement, sum of the voltages around the loop equals to 0. Here applied voltage V, first inductor across voltage E1, second inductor across voltage equals to E2. So KVL equation V minus E1 minus E2 equals to 0 or V equals to E1 plus E2. Okay, this is KVL equation for the above circuit. So next one, the induced EMF in first inductor. So the induced EMF equals to self-induced EMF plus mutual induced EMF. If only one inductor present, then only self-induced EMF is present. Here two inductors are there and which are placed very nearer to each other. So in each inductor, here self-induced EMF and mutual induced EMF are induced. So first inductor induced EMF equals to self-induced EMF plus mutual induced EMF. So similarly second inductor EMF equals to second inductor or second coil self-induced EMF plus mutual induced EMF. So first coil induced EMF E1 equals to, so first coil induced EMF L into di by dt. So here two inductors connection series connection. So the current in two inductors are same. It equals to I. So E1 equals to L into di by dt plus M into di by dt. So first term indicates the self-induced EMF, second term indicates the mutual induced EMF. So similarly second inductor induced EMF E2 equals to self-induced EMF L2 into di by dt, mutual induced EMF M into di by dt. Okay, let equation number 1 and it is equation number 2. So KVL equation V equals to E1 plus E2. So now substitute E1 E2 in equation 3, we get V equals to L1 into di by dt plus M into di by dt plus L2 into di by dt plus M into di by dt, or V equals to L1 plus L2 plus 2M into di by dt. So this is the equivalent circuit. So from this circuit we can write V equals to L equivalent into di by dt. So by equating these two equations we get L into di by dt equals to L1 plus L2 plus 2M into di by dt. Both sides di by dt cancel. So finally the equivalent inductance equals to L1 plus L2 plus 2M. In series aiding connection, the equivalent inductance equals to L1 plus L2 plus 2M. So next one, series opposing connection. Okay, here at dot marks the currents entering into the coil. So here see in first inductor here dot mark is there. So in first inductor from second end current entering into the coil. So next in second inductor here dot mark is there. So from first end the current entering into the coil. So this connection is called series opposing connection. In previous case, in first inductor current entering from first end. Similarly in second inductor also current entering from first end only. Here in first inductor current entering from second end, in second inductor the current entering from first end. So this connection is called series opposing connection. Here also the current flowing through the two inductors same. So let us consider two inductors L1 and L2 which are connected in such a way that the flux produced by the two windings is opposing. So if currents are flowing in the directions, then the flux produced by the two inductors are in opposite direction. Finally the resultant flux will decreases. So whenever AC voltage applied to the circuit, the current starts flowing in a circuit. So where E1 and E2 are voltage across the L1 and L2 respectively. So now by applying KVL, we can write V equals to E1 plus E2. So here E1 first coil induced EMF, E2 second coil induced EMF. So coil induced EMF equals to self-induced EMF plus mutual induced EMF. So here because of the current directions, the flux produced by the two inductors are in opposite direction. So the self-induced EMF and mutual induced EMFs also in opposite direction. So E1 equals to first one self-induced EMF L1 into dI by dt, mutual induced EMF minus M into dI by dt. So this mutual induced EMF due to second coil flux. Self-induced EMF is due to first coil flux. So first coil induced EMF E1 equals to self-induced EMF L1 into dI by dt minus M into dI by dt. So similarly second coil induced EMF E2 equals to second coil induced EMF L2 into dI by dt minus M into dI by dt. This is second coil mutual induced EMF. This induced EMF is due to first coil flux. Here minus M into dI by dt is first coil mutual induced EMF. So this EMF is produced by the second coil flux. Here two inductors are connected in such a way that these two inductors produces the magnetic flux in opposite direction. If magnetic fluxes are opposite, then automatically the EMFs induced also in opposite direction. So that's why here induced EMF equals to self-induced EMF minus mutual induced EMF. Okay, equation 4, 5, 6. So now substitute E1, E2 in equation 4. So equation 4, V equals to E1 plus E2. So V equals to L1 into dI by dt minus M into dI by dt plus L2 into dI by dt minus M into dI by dt. So this is the equivalent circuit. So from the circuit we can write V equals to L equivalent into dI by dt. So by comparing these two equations, can write L equivalent into dI by dt equals to L1 plus L2 minus 2M into dI by dt. So both sides dI by dt cancel. So finally L equivalent equals to L1 plus L2 minus 2M henries. So this is the equivalent inductance in case of series opposing connection. In series leading connection, the equivalent inductance equals to L1 plus L2 plus 2M. Here plus 2M in series leading connection and here minus 2M in series opposing connection. So in series leading connection, the equivalent inductance value high compared to series opposing connection. Okay, in parallel leading connection, already we derived. In parallel leading connection, the equivalent inductance equals to L1 into L2 minus M square by L1 plus L2 minus 2M. In parallel opposing connection, equivalent inductance value L1 into L2 minus M square by L1 plus L2 plus 2M. Numerators are same. In denominator, here plus 2M is there in parallel opposing connection, minus 2M is there in parallel leading connection. So similarly, in case of series leading connection, the equivalent inductance equals to L1 plus L2 plus 2M. In opposing connection, L1 plus L2 minus 2M. Okay, first this is series leading connection. This is also series leading connection. Here currents entering in both inductors from second end. Here current enters in both inductors from first end. So here in first inductor current entering from first end, in second inductor current entering from second end. So here also, so in first inductor current entering from second end, in second inductor the current entering from first end. So these two circuits are series leading connection and these two connections are series opposing connection. So series leading connection equivalent inductance formula, series opposing connection equivalent inductance formula. Okay, finally we can say that in series leading connection, in parallel leading connection, the equivalent inductance values are high, so compared to series opposing connection and parallel opposing connection. In leading connection, the equivalent inductance is more compared to opposing connection. Okay, now I would like to explain about the equivalent inductance in parallel leading connection and parallel opposing connection. Okay, these two circuits are parallel aiding connection. Okay, parallel aiding connection. So in this case here at these points, these are two coils, first coil and second coil. At these points the currents are entering in these coils, and here at these points the currents are leaving. So these two connections are parallel aiding connections. Okay, next here these two circuits are connected in parallel opposing connection. So first coil at this point current entering, and second coil at this point the current is entering, or first coil current entering at this point, and second coil current entering at this point. So these two circuits are parallel opposing connection examples. So next one, so parallel aiding connection, equivalent inductance derivation. So this is the given circuit. So here applied voltage equals to V, and first coil, second coil. So at these points currents are entering. So this connection is called parallel aiding connection. So first coil inductance value L1, second coil inductance equals to L2, first coil current equals to I1, second coil current equals to I2, and total current equals to I. So let us say we have two inductors L1 and L2 which are connected in parallel aiding connection. So whenever we apply AC voltage, whenever we apply AC voltage source to the circuit, the current starts flowing in a circuit. So let us say current I1 in the current flowing in inductor 1 or coil 1, and I2 is the current flowing in inductor 2 or coil 2. If we apply KCL, so here total current equals to I, first coil current equals to I1, second coil current equals to I2. So by applying KCL we can write I equals to I1 plus I2. So by differentiating this equation, di by dt equals to di1 by dt plus di2 by dt. Here two coils are connected in series connection, okay, parallel connection. So voltage applied across the two inductors are same. Here applied voltage equals to V. So finally here voltage equation V equals to VL1 equals to VL2. Current equation I equals to I1 plus I2. Voltage equation V equals to VL1 equals to VL2. So VL1 equals to, okay, first coil across voltage. Here first coil self inductance value L1, second coil self inductance value L2. The mutual inductance equals to M. So finally we can write VL1 equals to L1 into di1 by dt, L1 into di by dt, di1 by dt plus M into di2 by dt. Okay, similarly the voltage across the second coil VL2 equals to L2 into di2 by dt plus M into di1 by dt. So in this circuit the two coils are connected in parallel connection. So VL1 equals to VL2. So we know that VL1 equals to L1 into di1 by dt plus M into di2 by dt, and VL2 equals to L2 into di2 by dt plus M into di1 by dt. So by taking di1 by dt and di2 by dt common, we can write the above equation like this: L1 minus M into di1 by dt equals to L2 minus M into di2 by dt, and di2 by dt equals to L1 minus M by L2 minus M into di1 by dt. Okay, equation number 2. So this is the equivalent circuit. Here L equivalent is equivalent inductance of the parallel combination. So you can write here equation V equals to L equivalent into di by dt. From equation 1, okay, di by dt equals to di1 by dt plus di2 by dt. So V equals to L equivalent into di1 by dt plus di2 by dt, or L equivalent into di1 by dt, substitute di2 by dt here. So di2 by dt equals to L1 minus M by L2 minus M into di1 by dt. So by taking di1 by dt common, we can write the above equation: L equivalent into di1 by dt into L2 minus M plus L1 minus M by L2 minus M, or L equivalent into di1 by dt into L1 plus L2 minus 2M by L2 minus M. Okay, we know that V equals to VL1 or it equals to VL2. So use this relation V equals to VL1. So V equals to L into di1 by dt plus M into di2 by dt. Okay, this is VL1. L1 into di1 by dt plus M into di2 by dt, it equals to V. Okay, this is the V equation. So next by taking di1 by dt common, so L1 into di1 by dt, we can now substitute di2 by dt here. Okay, from equation 2 we are having di2 by dt equation. Okay, substitute di2 by dt here. So the above equation becomes L1 into di1 by dt plus m into L1 minus m by L2 minus m into di1 by dt. It equals to L equivalent into L1 plus L2 minus 2m by L2 minus m into di1 by dt. So now by taking di1 by dt common, you can write the equation L1 into L2 minus L1 into m plus L1 into m minus m square by L2 minus m into di1 by dt equals to L equivalent into L1 plus L2 minus 2m by L2 minus m into di1 by dt. So both sides di1 by dt, di1 by dt, L2 minus m cancel. Here minus L1 into m plus L1 into m 0. So finally the L equivalent equals to L1 into L2 minus m square by L1 plus L2 minus 2m. Okay, this is the equivalent inductance of the parallel aiding connection. So next one, parallel opposing connection. Okay, next one, parallel opposing connection. So here current entering at this point and leaving in this coil, the current entering at this point. Okay, if current enters at starting end in both coils or next end in both coils, the connection is called series aiding connection. Or in first here the current entering starting end, in first coil starting and current entering, and in second coil final and current entering. So this connection is called parallel opposing connection. Okay, let us say we have two inductors L1 and L2 which are connected in parallel opposing connection. So whenever we apply AC voltage source to the circuit, the current starts flowing in a circuit. Let us say current I1 in first inductor and I2 current flowing in inductor 2 or coil 2. So now applying KCL, we can write equation I equals to I1 plus I2. By differentiating this equation, we can write di by dt equals to di1 by dt plus di2 by dt. So here two inductors are connected in parallel connection. So voltage across the inductor 1 equals to voltage across the inductor 2, it equals to supply voltage. So equation, voltage equation V equals to VL1 equals to VL2. So next one VL1, here VL1 equals to L1 into di1 by dt minus m into di2 by dt. In parallel opposing connection, the resultant EMF value decreases. Okay, that's why here minus sign. Okay, in parallel leading connection, the self-induced EMF and mutual induced EMF in same direction and total induced EMF increases. In parallel opposing connection, so both are generates in opposite direction. Okay, self-induced EMF and mutual induced EMF are generates in opposite direction. So the resultant EMF value decreases in parallel opposing connection. So VL1 equals to L1 into di1 by dt minus di2 by m into di2 by dt. So similarly VL2 equals to L2 into di2 by dt minus m into di1 by dt. In VL1 equation, this is self-induced EMF and it is mutual induced EMF. In VL2 equation, it is self-induced EMF and it is mutual induced EMF. Here two coils are parallel connection. So VL1 equals to VL2. By equating VL1 and VL2, we get this equation. And here by taking di1 by dt and di2 by dt common, so L1 plus m into di1 by dt, it equals to L2 plus m into di2 by dt. So next write di2 by dt equation from this equation. Let it equation number 2. So this is the equivalent circuit. Here L equivalent is equivalent inductance of the circuit. So V equals to L equivalent into di by dt, or V equals to L equivalent from equation 1, di by dt equals to di1 by dt plus di2 by dt. So next to substitute di2 by dt from equation 2 here. So we get L equivalent into di1 by dt and di2 by dt equals to L1 plus m into L1 plus m by L2 plus m into di1 by dt. So L equivalent into L2 plus m plus L1 plus m by L2 plus m into di1 by dt, or L equivalent into L1 plus L2 plus 2m by L2 plus m into di1 by dt. Okay, we know that V equals to VL1 or V equals to VL2. So by using relation V equals to VL1, we can write, okay, first V equals to L equivalent into L1 plus L2 plus 2M by L2 plus M into dI1 by dt, and VL1 equals to L1 into dI1 by dt minus M into dI2 by dt. So substitute dI2 by dt here. So equals to L1 into dI1 by dt plus M into L1 plus M by L2 plus M into dI1 by dt. Or it equals to L1 into L2 plus L1 into M minus L1 into M minus M square by L2 plus M into dI1 by dt. Both sides dI1 by dt, dI1 by dt, L2 plus M cancel. So finally the equivalent inductance L equivalent equals to L1 into L2 minus M square by L1 plus L2 plus 2M. Okay, in parallel opposing connection, the equivalent inductance formula. Okay, in parallel aiding connection, here minus 2M is there, in parallel opposing connection plus 2M. So the equivalent inductance in parallel aiding connection is more compared to the equivalent inductance in parallel opposing connection. Okay, in parallel aiding connection, here minus 2M. In parallel opposing connection, here plus 2M is there. The equivalent inductance in parallel aiding connection formula, L equivalent equals to L1 L2 minus M square by L1 plus L2 minus 2M. In parallel opposing connection, L equivalent equals to L1 L2 minus M square by L1 plus L2 plus 2M.